a proposition we had last week, which was the direct sum criterion. And that said that if we had subspaces u1 up to um of a vector space V, then V was the direct sum of these subspaces if and only if, so IFF stands for if and only if, first of all, V was the sum. That is, every element in V could be expressed as a sum of elements, one from each subspace. And two, there was a unique expression for 0. And since 0 is in every subspace, the unique expression, which is just a sum of a 0, with each 0 lying, thinking of it as each copy of the 0 vector lying in a different vector space, subspace. That was one example, and that was the only example if it was unique, right? And so we found that it would be cumbersome, of course, to check that every element of V had a unique expression by enumerating it or by some other method, but this means we only have to check that one single vector, the 0 vector, has a unique expression. And so what we want to do today with the ideas of linear span, linear combinations, and linear independence is kind of take that idea and specialize it to the case that each of these subspaces are just one-dimensional spaces that are spans of a single vector. So think about each ui is going to be a scalar multiple, the set of all scalar multiples of some single vector, vi. You want to think about a vector, and then you have all of its scalar multiples. We're going to specialize to that and think about this theorem and the idea of a direct sum in that setting. That's going to lead to the ideas of linear independence and dependence, which are almost the same, but just sort of phrased slightly differently. So let's make the definitions. Let V be a vector space over a field F, and V1 up to Vm, a list of vectors in V. We want a matching list of field elements Now, the distinction between list and set is that a list can have repeated elements and it's ordered. A set can't have repeated elements. So, if I'm just thinking about numbers, for example, that's a list. And the set of things that appear in it is just 1 and 3. I don't care about the order. Now, you'll see lots of textbooks talk about sets of linear vectors and linear combinations of sets of vectors, and we'll talk about that as well. The reason that Axler is using a list is that it just makes certain definitions simpler. But don't worry about it too much. It's not a huge distinction. That won't really factor in that much. So we have a matching list of vectors and field elements, and we call a vector V, which is a sum of scalar multiples of vectors by corresponding field elements. This is what we're defining here. This is a linear combination of the vectors V1 through Vm. Okay. So I'm going to make some observations. Take this set of all scalar multiples of some particular vector V, with V V1 is an element of the vector space. This set is a subspace of V. Maybe you could call it, big V1 or something. It's a subspace of V, which is the span, which is the sort of the ray. It's this subspace here. So we know that if I take, from the discussion about sums, that if I take multiple subspaces, V1 plus V2, that's a subspace. V1 plus V2 plus V3, that's a subspace, and so on. So therefore, since these are all subspaces, and I can say this just as easily as I can say this sum, the set of all things, the set of all linear combinations of a list of vectors is itself a vector space, and it's a subspace. So I claim that if you think about it a little bit, it's easy to see. The list, or the set of all things of this form, of all linear combinations, of a list V1, Vm of vectors in our vector space V is a vector space, and it's a subspace of V. Essentially, that's because we've defined it as things that I can write as a sum of elements, one in each of these. And we know that each of these things, when I vary A, is a subspace. Right? So it's just something like this. And since it's a subspace, it has the same scalar multiplication, it has the same addition, and so on. And the reason I mention that is that we want to say that this subspace, or vector space, of linear combinations of a list, V1 up to Vm of vectors is called the span of that list. It's the subspace, which is the sum of the individual spaces. M set of all vectors, which can be written as a linear combination. With the coefficients in the field. And by the way, in this idea of a linear combination, these AIs are called coefficients. That's the coefficient of V1, the coefficient of V2. This list may have redundancies at this point. They may have multiple copies of the same vector. So the coefficients, we may have two different coefficients that go to the same vector, but it's two copies of the same vector because we're thinking of it as a list. And this span is, okay. So how about this list of vectors? What's the span of this list? So related to the, what is the sum of 0 things? Or what is the product of nothing? What is the empty product? What is the empty sum? So the empty sum is 0. It's the identity element. The empty product is 1, the multiplicative identity element. The span of the empty list is the kind of the identity element in our monoid of vector spaces. So the span of the empty list, it only makes sense to make that the 0 vector space. Okay. Or you could think of that as a convention if you don't sort of believe this principle. And if you like definitions, so we said that for everything, or most things in math, we have a constructive definition. Like it's the set of all things with this property, or they can be written this way. And we have a sort of implicit definition or axiomatic definition, like the solutions of a set of equations or a linear equation, the set of all things which dotted with a vector give me 0. And similarly, we can make a definition like that for span by observing that the span of a list of vectors is the smallest subspace containing every vector in the list. Okay, so we already saw that you could think about, right, if I have a bunch of subspaces, V1, let's make them U, U1 up to UM, subspaces of V. We already saw that, this concept of union is not the right concept, right? I could take the union of all these spaces, but then I won't get a vector space. Instead, I should take the sum, which is the smallest thing, which is a vector space and contains this. This is the same statement again, but about just vectors, right? Because I could have just said, so now I'm saying I'm only going to not even think of whole subspaces, but just vectors. So I want the smallest subspace that contains these vectors of my list, V1 up to Vm. Actually, I can think of it as a set here because I don't care about redundancy. It's a vector space, so if it contains one of these, it contains all multiples. Right? It contains this vector and that vector. It contains all multiples in both directions. So actually, I'm saying it's the thing which is the which contains this, all multiples of this. So that's a subspace. It contains all multiples of this and everything in between. So it contains the union of all of those things. Okay. U1 union union UM. Okay. Contains the union of all of those multiples, and that's back to this. Right? So this is the smallest subspace that contains every vector in the list, or every scalar multiple of every vector in the list, or every subspace generated by every vector in the list. Okay. So we've talked about finite and infinite dimensional vector spaces from the beginning as examples without actually giving a definition. And so now, because we've broken up our vector space in some sense into things we can count, individual vectors, we can actually give a definition, not quite of dimension, but at least of finite versus infinite dimension. So I want to say that a vector space is finite dimensional if there exists a finite list V1 up to Vm of vectors which span the space. So that wouldn't have been helpful if I was just talking about subspaces because, well, I could just take the subspace, which is the vector space itself. Right? Every vector space is spanned by a finite number of, or is a sum of a finite number of subspaces, namely that vector space plus 0. So until I had this idea of one-dimensional vector spaces, things which are just the spans of individual vectors, it doesn't make sense to talk about finite and infinite dimensional. So now we can say that a vector space is finite dimensional if I can pick finitely many vectors that span it. And otherwise, so if there is no such list, it's infinite dimensional. And at this point, we're making no distinction between countably infinite dimensional, like polynomials, univariate polynomials, and uncountably infinite dimensional, like vectors from, or functions from 0, 1 to r. Both of those things are infinite dimensional, have no finite spanning list. Now, even though a infinite dimensional vector space doesn't have a finite spanning list, we can take finite subsets of it. We can take subsets of it, and we can take finite lists of vectors in it and write their linear combinations and still say something that makes sense. So we say that V in V, which might be infinite dimensional, is a linear combination of elements S in V. So I'm thinking of V as infinite dimensional, and here I'm just saying S is just required to be a subset of V, right? Subset, not necessarily a finite list, but it's a linear combination of elements in this subset if there exists a finite number of elements u1 up to um in V, and scalars, matching scalars, a1 up to am in the field, which V is an F vector space, such that V is equal to a1 plus u1, a linear combination of this finite set of vectors, finite list of vectors, am, um. And we can define the span still of S of all such finite linear combinations. As long as we only talk about finite things, we can make a choice of a finitely many vectors in our linear combination. It still makes sense to say that. So for example, if I consider the set 1, x squared, x cubed, x to the fourth, and so on, and I'm thinking of that as a subset, an infinite subset of the space of univariate polynomials in one variable, the polynomials are exactly finite linear combinations of these elements, right? If I take any finite linear combination, finitely many of these, and I multiply each by a scalar and I add them together, I get a polynomial. If I'm allowed to take infinitely many, then I can get other things, right? Then I can get power series, I can get, exponential function or whatever, right? By calculus sort of considerations. So I don't want infinite linear combinations because that's going to get me out of this vector space. The finite linear combinations of this infinite set are just fine, right? And I could, I can take fewer things in here. I could say throw out all the even degrees. Oh, I should have put x in there too. 1x, x squared, x cubed, right? I could throw out all the even things except 0 and take their span, and then I would get polynomials that have even degree. Or 0, right? That would be a proper subset, which is a span. Okay. So now let's make some definitions that have to do with uniqueness of this representation, uniqueness of the expression for a vector in terms of some list of vectors. So consider a list v1, v2, up to vm of vectors in V. And U in the span of this list. In other words, U is equal to A1, V1, plus a bunch of others, plus AM, VM for some choice of field elements. And we'd like to ask, this is an expression for this. That's like an expression we'd have in a sum of subspaces. And when is this expression unique? And we're going to get a similar criterion as we did with sums of subspaces, that what matters eventually is how we write 0. And the reason for that is if suppose I have another expression, b1, v1 plus etc. up to b sub m vm. That's another expression. I can use my additive inverse and distributive properties to write that u minus u on the left-hand side is equal to on the right-hand side after using the distributive a1 minus b1 times v1 plus a2 minus b2 times v2, so on up to am minus b sub m vm. Right? And this expression was unique if all the AIs were all equal to all the BIs, that is, if each of these things was just 0. That's a 0 field element, by the way, right? So unique if these AI minus BI are all 0. If some of them can be allowed to be non-zero, then it must be that that expression was not unique. So that motivates the definition of linear independence. A list v1 up to vm of vectors in a vector space V over a field F is linearly independent if the only choice of A1 up to AM, which makes A1 times V1, this linear combination, equal to the 0 vector. The only way that I can write the 0 vector as a linear combination of the vectors in the list is setting each coefficient, each field element, equal to 0. And if that's the case, that is, in the case of linear independence, each vector in the span of V1 up to Vm has a unique representation. And I hope you can see this is really just a sort of specialization of what we did for sum and direct sum. Let's give an example, then I think we'll stop for today. So if I think about F2, or let's say R2, that is pairs of vectors x, y, with x and y both in R, with the element y's addition and the broadcast scalar multiplication. Then this list of vectors, 2, 1, is linearly independent. That is, there's no choice of A and B such that this expression is equal to 0, except for A equals 0 and B equals 0. On the other hand, if I added one more vector to that, one, 1, 2, 1, and 1, 2, say, there is a choice of 3 coefficients. I could take 3 times 1, 1 minus 1 times 2, 1 minus 1 times 1, 2, and that would be equal to the 0 vector, 0, 0. So there is a choice of non-zero ABC such that I can write the 0 vector. And so these 3 would be called linearly dependent. And you should notice that, we think about this as being kind of a 2-dimensional space. I can fit 2 linearly independent vectors. You might expect that it's hard to fit more than 2 linearly independent vectors in that. And that's going to be the strategy we take to actually define dimension, not just finite or infinite, but exactly what dimension it is. And that's what we'll start with on Friday.